Okay, let's do some homework from section 6.6. The exponential part of section 6.6. So problem 3, I can understand why this is giving people trouble. When I wrote it down, I wasn't trying to trick people, but it is kind of tricky. What makes it tricky is that there's something you can do which makes sense algebraically, but which won't give you the correct answer. And that's okay. You see that we have stuff we don't want on the left. Let's get rid of that 3 via subtraction. And now we don't want this power. So let's take the logarithm of both sides. Oops, this isn't going to work. The logarithm of -4 isn't defined. We can't do this. What we could do instead is take this -5 over to the right, and then it's positive. And we can take this -1 over to the left, and then it's positive. And then this problem becomes probably relatively straightforward. We take the logarithm of both sides. On the right, the x comes down. We divide both sides. And then whatever the natural log of 4 divided by the natural log of 5. I've lost my calculator. There it is. Let's try to share it. Get rid of that. The log of 4 divided by the log of 5. About 0.86135331. So as I say, that problem wasn't intended to be as tricky as it was with this kind of false start. I just wrote it and didn't quite think about the way that it could go wrong. You have to stuff has to be positive if you're going to take its logarithm. The next question I was asked about is 7. So let me see. This is visible on the document camera. So the atmospheric pressure is this. That's quite a decimal. It looks like 3 zeros, then 1 to 8 to D. And in Mount Everest's so-called death zone, which is somewhat more less dramatic than it sounds. Obviously, people do not keel over dead when they climb Mount Everest, but in its death zone, the atmospheric pressure is 337. And we want to find where the atmospheric pressure is 337. That is to say, we want to solve this equation. So, what to do? At some point, we're going to have to take a logarithm. Our variable is in the exponent, this D. The way to get a variable out of an exponent is to take a logarithm. Probably don't want to take the logarithm with this number sitting here. If we take the logarithm of this, we've got the logarithm of a product. We have to break it apart. It's a whole thing. Probably the easiest thing to do is to get rid of that number via division. And now that we just have an exponential over here, we can proceed. And we can take any logarithm that we want. The most natural, if you'll pardon the unintentional pun, the most natural logarithm to use is the so-called natural logarithm. And the advantage of the natural logarithm here is that the natural logarithm is base e. And when our bases match, the logarithm and the exponential just cancel each other out. If you wanted to use something like the common logarithm, you could, But instead of the logarithm and the exponential canceling each other out, you'd have to take that down in front of the common logarithm and do some division. Using the natural logarithm spares you from having to do a division step. But there is still a division that needs to be done. Here's a D, what we're trying to find. It's being multiplied by this number. We'll finish this problem out. Like so. And if we want to get a decimal approximation, which we definitely do, because if you tell somebody that you're going to climb the natural log of this fraction divided by this decimal, they'll have no idea what you're talking about. The natural log of 337 divided by 1013 divided by negative 0.000128. We are looking about 8,598 miles above sea level. Let's see. We're not gonna do both 10 and 12 in the next 5 minutes. I don't mind going a little long if people have places to be. Of course, they can head out. Let's do problem 10 next. An investment of one. So let's just write down the equation for the value of the investment. An investment of $1,000, the principal goes there, times 1 plus the interest rate written as a decimal divided by the number of times this is compounded, raised to the number of times it's compounded, times T. There's the value of the investment. And you want to know when it's worth $1,700. So Very similar to the last example, we probably don't want to take the logarithm. Well, we've got that multiplication there. We do want to take the logarithm ultimately. That's how we get time out of the exponent. But let's divide both sides by 1,000 first. And let's go ahead and in the same step, let's take this sort of ugly thing we have here and let's simplify it. This is 1.000675. And now we can take a logarithm. It scarcely matters which one. We could, for example, take the natural logarithm of both sides. On the left, remember that cancellation we saw in the Everest problem only occurred because there our base matched our exponent. Here our bases don't match. We've got base E, base 1.00675. So the natural logarithm doesn't go away, but the power comes down in front of it. And what I was saying, where's that Everest problem here? When I was saying that using the natural logarithm spares us a division step, here, because the logarithm and the base don't match, we've got this natural logarithm that we have to get rid of. And because this is multiplication, it's gotten rid of via division. And then we've got this 4, which we also have to get rid of, again, via division. And let's see if we can do this. The logarithm of 17 divided by 10 divided by the logarithm of 1.00675, close both the parentheses, divided by 4, about 19.7 years. One more problem, problem 12. So maybe I'll speed through this a little quicker because we have had our 50 minutes, but also because this problem is so similar to the two problems we just did. We have an exponential. This exponential represents population. We want to know when the population is 200. So once again, we're going to have to take a logarithm, but we don't want to as long as we have this multiplication. So let's divide both sides by 1,500. Take the natural logarithm. We could use the common logarithm if we wanted to. But taking the natural logarithm, the logarithm and the base cancel, and you would just get cancellation. And then I'm out of space, so I won't write this down, but we'll divide both sides of this equation by this decimal. The natural log of 2/15 divided by negative 0.29598. 6.8. So how would we interpret that? Let's see, what does the problem actually say? This is not the screen I was trying to share. I was trying to share the screen with the assignment on it. T is the population after 1864. So I guess it depends on exactly like after the beginning of 1864, after the end of 1864, but 6.8 is about 7 years, so about 1871, I'd say. The population was reduced to 200 people.